Hello, folks. It's George Leoniak, and welcome to New Geometry. I'm super excited to be here sharing another video with you today. And today we're going to talk a lot about the Icosiedodecahedron, the Archimedean solid that has 12 pentagon faces and 20 triangular faces. It's composed of the 10 decagons and hexagons in there as well as the squares that are making up the vertices of the octahedron. So we're going to learn a lot about this form, and part of it is going to show how a form like this in compound form made this completely new geometric polyhedron that I'd never seen before, with this irregular nonagon faced nine-sided polygon here and decagon faces. So we're going to learn a lot about this, and towards the end of the video, I've got an awesome other form that came about through all this exploration. So I'm going to hop over to sharing the screen and do the presentation related to this to show you how I ended up there and learn a little bit more about what this Icosiedodecahedron is. Now, if you're somewhat familiar with sacred geometry, the cube octahedron, which is this form right here, the vector equilibrium, is can either be thought of as a cube, regular cube, or the octahedron, where the vertices, the edges are truncated at the midpoint, leaving the remainder of this form. And you can do it for either. Now, the Icosiedodecahedron is really the same concept of truncating the edge points in the middle. So this is your Icosahedron in blue. At the midpoint of that edge, if you do that all the way around, you're going to create these triangular faces within the triangles of the icosahedron. So here's your 20-sided icosahedron. It's right at the midpoint. We'd be making another triangle. And if we take that form out, we're going to get left with those 20 smaller triangular faces and making the large pentagons that you could see are being created here. Now, the same thing will happen either way with the icosahedron or the dodecahedron. So if we do the same thing here, truncating those pentagon faces at the midpoints, we're basically creating a smaller pentagon, as you can see here in the black, in the larger red pentagon face there. We take that all the way, take off those little pieces that we've truncated off, and we're left with this Icosiedodecahedron. Very, very cool form. Now, I want to back up to some previous videos that I did, and this is kind of what led me to figuring out how to construct a compound of 6 Icosiedodecahedron, what makes up that polygon, the polyhedron over here with the 9-sided faces that showed up on it. So what I did here in this video called the dodecahedral compound transcends the limits of Metatron's cube, new level of sacred geometry, always throwing in the KNEW in there whenever I can. Well, the reason I brought in Metatron's cube is because Metatron's cube is, as I've said in many of my videos, doesn't draw you an accurate dodecahedron. So you really miss out a lot of what sacred geometry can offer. It's like, you know, it's not going to the party, basically. And basically, it's just hanging out with cubes and octahedrons, but all that fun stuff of life, the icosahedron and dodecahedron, they're left out of that picture. So when I discovered how to actually draw that accurately, it opened up this whole spectrum. I'm not showing the golden circle seed of life, which I call it. You'll see it in a few slides. In fact, let's just jump back one. This right here is the golden circle seed of life, which just easily draws the Icosiedodecahedron and the dodecahedron icosahedron, not possible in the regular, just non-phi ratio circle template that just does cubes, octahedrons, cube octahedron, things like that. So anyway, when that gave me this ability to start working with the dodecahedron, and actually came up with another view here to draw the dodecahedron and make this compound. So that's a whole other video you can check out. And I also did that with the icosahedron and made this compound 6, which made this culminating form of all of them together. So both of these, when you kind of connect the vertices of this kind of woven tangle of compounding that's been going on here, what happens is in the end, you'll connect the vertices and you'll come up with a pretty nifty looking form. All of these edges and angles all add up to sacred geometry, sacred roots, and things like that. And this one actually turned out to be the inner hull of a truncated icosiedodecahedron, a true truncation of the icosiedodecahedron, making these golden rectangle faces around the pentagon. So this little woven tangle here turns out to be this when we connect the vertices. So really, I took these forms, I started out this way, and I did it with the dodecahedron. Basically, I went around and went to the midpoint of each one, creating these little smaller pentagons. This is all hand-drawn. I had to do this all hand-drawn here. To basically put all these icosiedodecahedron. Let's go back here to the dodecahedron version. I'm just truncating around. I do it on this whole thing in here of, finding all the pentagon faces until finally I come up with this. So this is the 6 icosiedodecahedron. Now, there are 6 in each of these, and there are, typically this would be considered a compound of 5, but I noticed there was an invisible icosahedron, an invisible dodecahedron that's actually created by the vertices of the 5. So when you do the 5 compound, you automatically get a 6th, and that was always the center of the drawing. This is the oriented drawing one, but the other ones basically created that one. So you probably would find in the literature compounds of 5 dodecahedron or 5 icosahedron, but at least the way I discovered it, there are 6 that are really in there. It's just the last one in there is not really necessary for the form. Same thing here. This icosiedodecahedron is in here. It's not necessary for the final form, but it is included because it adds to the compound of 30 octahedra. So there are actually 30 octahedra in here rather than just having 25. So I don't know, this has something to do with the sacred numerology that or the numbers that are associated with the 30 of the octahedra that are found within this. So let's talk about the form for just a moment. And, the crisscross of lines, basically what's happening here, if we were to, I'll zoom in on this so you can take a closer look at the face. Let's go into 200%. And the colors that are crisscrossing. So here's a decagon face. So the form is made up of 12 decagons rather than just the pentagons that are normally shown on the icosiedodecahedron. And the decagon face is made of each of these 5 edges that are going to show up, the black one, the blue one, I don't know, the light blue one, regular blue one. They're all crisscrossing here. So each is adding one of these edges, this edge right here, to this whole form. And in the middle, there are the triangles of the red one and the black one that are at the center of the form. And this is what I call the invisible icosiedodecahedron that is basically meeting all the midpoints at the intersection of those isosceles triangles. So really, I didn't create this form. The form created itself. I mean, I just kind of saw what happened with the compound, and this is what it did. So it created the 9 faces on its own without me having to do anything, because this is a nonagon, irregular shaped nonagon, meaning it has 9 edges on this polygon and this isosceles triangle, and created the decagon faces all on its own just by following the rules of 5-fold symmetry here, with the 6th one being in the middle. So it's got the 20 nonagon irregular faces, 60 isosceles triangles. We'll talk about those in a moment. And it has 150 vertices. Now, you're probably, if you're doing the math, the icosiedodecahedron has 30 vertices. So if we have 6 of them in there, 6 icosiedodecahedron, you would say, oh, it must have 180 vertices, but it has 150 because this central one, the 6th one, is sharing the vertices of all the combination of the others. So it doesn't have its own unique vertices that it's contributing. So it comes up to 150 vertices. And I really like the balance of the edges, 240 edges, 120 are a 1-inch edge, and which is the decagon has the 1-inch edges. And then that edges of those isosceles triangles, 2 of those edges are square root of 2 at 120 of those as well. Of course, I love to build and draw these forms. So I first constructed the model, and which is this one here, and it's very neat to see it from a few different perspectives. I haven't discovered how to draw yet. I think they're going to be quite complicated, but at least from the hexagon view, I did come up with the line drawing method within the golden circle seed of life to figure out all the lines that would be necessary to draw it. And it's a very doable drawing. In fact, Danny Burgess on the new geometers, I gave him the circle template and the line drawing, and he was able to draw this and post it. So it's very neat to see that this new form based on sacred geometry and those compound of 30 octahedron, 6 Icosiedodecahedron is part of the pattern language of sacred geometry through the working it into the circle template and line drawings that it can be done with. So really neat for that to come about. I'll just say, though, it was a kind of backwards compatible, like I had to fit the circle drawing to discover the line pattern rather than do the circle drawing and then figure out the lines. I think this, if you did this, saw the lines very up close and all the circles here, you'd be like, how do I even, like, what connects to what? I mean, I'd be super amazed that someone would find this in all these circles and lines. That would be quite incredible. And then to build it. But what I did was actually I had this done, and then I was like, okay, let's apply the golden circles and figure out how this is going to be found within it. So it was kind of a reverse situation that took place. I just want to briefly touch on the mathematics in this a little bit, and this is going to relate back to my previous video, which we're not really talking about much here, other than the Archimedean solid, the Icosiedodecahedron, but I did a sweet video on drawing 11 of 13 Archimedean solids. Some of those were related to this circle template, which includes the golden circle seed of life. So if you don't know what that is, it's basically the seed of life pattern with the 6 blue circles around the central blue circle, including these phi ratio circles. So that's the golden circles, and it's the seed of life pattern. And then I did these root 2 circles. And this pattern just contains all these sacred roots 1 through 7 easily in here. And I just wanted to illustrate that this brought me back to that because I wanted to find out more about that triangle that is this yellow triangle here. That what was the properties of that? And I didn't know how to go about figuring that out, but I just said, hey, maybe it has to do with the square root of 2. So I put a little square at the bottom of this, and I drew my diagonal across the square face, swung it up, and it turned out to be the exact triangle I needed. So that's how I figured out that it was root 2, 1 to root 2 for that isosceles triangle that makes up the whole form. And just so happened that this whole diagram includes that measurement. That square root of 2 measurement is right here off the 1-inch edges. So you can take a look at this and just look at the roots of where they are. Of course, root 2 and root 3 are the blue and the, I think is the red one here. And it was very cool to see root 7 show up here, the square root of 7, which is actually the length of 2 of those triangles. And I just love that this was 41.41 degrees right on the nose for the angle of this isosceles triangle. The square root of 5 is found in here, so we're going to get our phi division, which we know this golden circle pattern has. And we can even get root 6, but we have to reorient root 5 over along this horizontal line and pick up root 6. So just this template itself just contains sacred geometry and sacred mathematics all within it. Check out the Archimedean solid video. I didn't have this diagram in it specifically, but I talk a little bit more in detail. And this 1-inch edge, if it's on the the form, well, that's the same edge here and here for the three faces types that we have for the big solid here. Those are the three faces, and they include the 1.618 at the radius here. The diameter would be times 2, so 1 to 1.618, and the 9-sided polygon is also picking up that measurement as well, because those are actually the edge lengths of the Icosiedodecahedron. So those with blue edges would be going across the faces, like back here. So, whoops, this one here, the edge length here and the edge lengths there. That would all be the edge lengths of the Icosiedodecahedron. Okay, so moving along here, just, I like to turn this into just look at it from all angles, see the front and back of the form together. What does it look like when we're not just looking at it from one view? And I thought it made a pretty sweet pattern, very, love the shape of this 6-pointed star in the middle. So this has got the decagon face and the nonagon faces overlapping one another to kind of create a more geometric mandala-like pattern that can emerge from this, with plenty of cool coloring options in there too. Definitely a tricky one to draw, but it is definitely doable by hand. All right, so this was another kind of area of exploration. I know that the Icosiedodecahedron, the shape, when we draw it from this perspective right here, if we put a circle around this hexagon, 1, 2, 3, 4, 5, 6, that circle is actually in contact, is actually the sphere that would be around all the vertices of this form. It just so happens nicely in this Icosiedodecahedron drawing, it doesn't happen for too many forms, that hexagon, flat hexagon, is actually showing the vertices that are in contact with the sphere that it would be contained in. So I wanted to find out what was up with the whole form, how many vertices were in contact with a sphere, because there's 150 vertices that are in contact with the sphere. And remember, there's 6 Icosiedodecahedron around it. So from this view, just from this hexagon view, it picked up 18 vertices that go around in this type of arrangement. Now, it was very surprising to me that, like, how amazing this was with just the basic seed of life pattern. I'm not even adding phi ratio circles. I'm adding the half the radius circle of the big circle. So I'm basically putting a half a size circle in here inside each of these. So these circles are basically the 6 around 1. If you take 6 pennies and put 1 penny in the middle and put them all together, all those edges will touch. So these aren't the phi ratio circles. They're just fruit of life circles and seed of life circles. I'm able to find those vertices on that outer circle. That outer circle is right here at those vesicas, right? So that's what the Icosiedodecahedron is within. I'm not drawing the Icosiedodecahedron here or this complex form at all. I'm just saying that already in the basic sacred geometry that exists here, I can extend this red line of number 18 here, and it basically has to intersect the petal, the big flower petal here. It intersects the small circle and those little black dots that I've done there. If you did that all the way around, you would actually create the vertices of this form. It's right there. You're actually creating the vertices of the compound of 6 Icosiedodecahedron right here and you would never even know it, really. I mean, I've never decided to draw a line there, but it just so happened that just by finding that little segment between the seed of life petal and that circle, very easy to draw this without doing this whole complex thing at all. Automatically, you get 18 and 24 divisions. It's not an equal division of the circle here, so it's not 24 equal segments, but it does lay out the potential that, hey, look, there's 6 Icosiedodecahedron. Basically, there's 30 octahedra in this. It's a big jump from the 1 octahedra in the drawing to thinking that there are a compound of 30 octahedra in this drawing, in this beautiful arrangement of mega compounds here. And of course, it could compound again. You can compound that whole form, but I'm not going there. It's too much of a big compound for me to take on, I think. Maybe. So I'm just following this out. So, every morning I'm waking up with maybe a little new insight, some trail to follow and check out and tinker around with. And then I was like, well, okay, in this Icosiedodecahedron, it's such a beautiful polyhedron that it contains the octahedrons, right? Remember, it contains a compound of 5 octahedron. That's what makes this up. 5 of these rotated around, hit these vertices. Each of those 5 on that pentagon face are basically this octahedron going 1, 2, 3, 4, 5. 5 of them, right? So you got 5 in there. And this form, of course, is basically just made up of 3 squares. 1 square, 2 square, and there's the other square. So we got 3 squares in there. So that means that there's 15 squares in this. Now, if I then say, hey, how many are in the big compound of 6? That gives us 90. Okay. Now, there are also hexagons in here, but let's talk about the decagons first, because the decagons are easy to find because they're just the edges of the form itself. There are 6 decagons in here. So as I rotate this around, we could just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm back. So I've got these 6 decagon hoops. So I've got the 4, the squares, right? And I've got the decagons. And now the hexagons are in here too. And basically, if you make stars on each of these faces, those stars, right, the pentagram stars, if you're doing that all the way around, those will create the hexagons. And I got really interested about what's going on with those hexagons. So let's just first do the math with everything, which I thought was very cool because we're going to get 90 for the compound of 6. 10 are in the regular Icosiedodecahedron. Now we've got 60 in the big one. And then we've got 6 in the regular Icosiedodecahedron of the decagons, right? And then 36 total in the compound of 6 Icosiedodecahedron. I didn't realize this, but, as I was just thinking about, while putting the presentation together, I was like, wait a second, 90. So the central angle here is 90. The central angle here is 60. The central angle here is 36. It's just amazing to me how the numbers just added up to the same amount of polygons, these polygons that are in this big compound of 6 Icosiedodecahedron. They're actually the same numbers as the central angles of the polygon shapes themselves. It's just, magical stuff. So I woke up that morning and I was like, let's take a look at these hexagons. And I started to draw this before I knew anything about what it was. This is an interesting drawing out here. You might want to just pause your screen for a moment and maybe see if you could just pick up one hexagon. Like there's 10 hexagons that I drew first here. And basically you could see the crisscross of the stars because I just went around an Icosiedodecahedron outline and just drew in the stars. But I had to do the back of it too. So we're getting stars on the front and the back. And the easiest hexagon, of course, is the one that's in contact with the sphere. So that's the big blue one around the edges. And a more obscure looking one, let's just say, would be this one here. Oh, this short little blue edge goes over to here. They're crisscrossing other hexagon edges. This one goes over to here, this one goes over to here, goes back to here, and connects back. So believe it or not, that's another hexagon. I have a sheet of hexagon here. It's just kind of facing you in kind of a skewed angle, something like that, We're not seeing it like we normally do. But this is really what the beauty of this template of what I'm saying does, is with all this phi ratio that adds to it, it's allowing us to like project the flat hexagon view that we see in the Seed of Life design. And you know what, we can do this with the cube octahedron, of course, in there. We can see those hexagon faces from other angles. So basically what I did here was I am basically constructing the hexagon version, just like this is made of 4 hexagons. There's the big one that we're looking at. And then we've got one that crisscrosses this way, one that goes down. So we got that one, and then we got the one going along here. That's 4 great circles, that's called. Well, this is going to have 10 great circles. So we're going to have 10 great circles. And just to back up, if we're going to have 10 great circles here, we're going to have 6 great circles because of the Icosiedodecahedron here. And this one is going to contribute the other 15 great circles, I guess, for each of these squares. So that's going to equal up to the 31 great circles of the Icosiedodecahedron. If we put all these all together, this form will create 31 great circles. That's so neat. It's not the same 31 great circles that Buckminster Fuller did, but I guess the Icosiedodecahedron will create 31 great circles all on its own. So these forms here that I did here, I discovered about half an hour before I decided to do a little research. And Wenninger's book, this is just amazing. The Monk, Magnus, polyhedron models, dual models, spherical models. These fellows were just amazing. Coxeter and Alan Holden in this book. In like taking sacred geometry from the way it's really presented now and bringing it to a whole nother level. It's just, the thing is they didn't really teach you how to draw this stuff in sacred geometry. All of it's about the polyhedra and building the forms and things like that. But they're using sacred geometry to even get there in their templates. So it's all sacred geometry. Yet in terms of our ability, a person with just your compass and straight edge, and not just drawing templates to cut out squares and circles, squares and these shapes to make the polyhedra, but how do we depict the form in the circle template? Because we often say, Metatron's cube contains all the 5 platonic solids. Not true. The golden circle seed of life, yes, it does contain them. So how do we depict it? Well, we have to add the phi ratio to a form to create it like this. So long story short, I decided to draw this form out. And basically you can see that these are the hexagon edges that would be going along here of one hexagon. And here it is meeting another hexagon that's going along as well. And they're creating these little seams that are going down into the middle of the form. And there's creating a shape all the way through. And this would be convex going towards the center. And everything is meeting at the center here. All 10 vertices are coming together at the central point. And it's called a nolid, like a solid, but it's no, there's nothing there. There's no volume to this form. It's a polyhedra that has no volume. It's totally open. And it has no dual form, really, although Wenninger shows how you can create a dual form from this. But what happens is that the vertices of those dual forms will recede or extend into infinity, and even writes in the book that that line that's going into infinity will loop back around and come back in to create the line that comes back to the form. It was like, wow, way out there stuff, but very interesting to contemplate that the forms we're drawing, or at least these forms, open up this doorway to infinity. And it's really an icosiedodecahedron hull, but just looking at those hexagonal slices, we can do it with the square slices, and we can do it with the pentagon slices, the decagon slices. So this is just a really amazing form. Or thinking about geometry not as solids, but as actually pentagonal, square, and decagon slices kind of overlapping, creating the vertices of these forms. So here is the drawing I did. I did it without the central pentagon lines, but I tried to color this so maybe you can kind of follow along and pick up which hexagon is which in this. It's not colored in the middle, but it's going to go through these as well. So you can have some fun trying to tease out where the hexagons are actually in there. And so in my research and discovery after drawing all that, I was like, I'm sure that Weninger and Coxeter figured this out. So in his book, he's got a picture of the small dodecahedron icosahedron, which basically just capped that off with a star. But you can see that that hexagon is going to go around. And I was blown away when he showed that this hexagon right here is a 5 proportion division. This is what I mean. This golden circle seed of life is basically what these fellows are using to create all these templates for the star polyhedra, which this is considered a star polyhedra, and other forms. Here is the one example in the book of how this hexagon is divided into it. And it's the same hexagon that I've been talking about for almost a year now, that is how to draw the dodecahedron. See, the black, so here's the red is the dodecahedron. Here's that big hexagon. I've just rotated it 30 degrees, so it's oriented up, like, so we can see the dodecahedron normally, how we see it. So there's the edges of that. These are all the golden circles. And these are the lines that are radiating out from the center that are the same 5-divisioned hexagon that basically draw this form. And it also is right here, the Icosiedodecahedron, which is this form, is in the template. So not only is the blueprint for constructing this form, in this, it's also the template to draw the forms as well. It's both. It is totally the template to draw and build, at least particularly for this form. There's other forms in there that you have to use other techniques, but this one clearly showed how it was the template was what you needed to do it. And the Icosiedodecahedron, as I've been saying, because it includes squares, decagons, and hexagons all within this, what a great template to build from. So here it is. I just, like, if we were to cut out these 10 hexagons, which I did, in a moment you'll see, those 10 right there are the ones we need, and it's all drawn right in the golden circle template, just expanded to pick up all the places. And here are all the little connecting lines, just like this drawing here. That is what they drew here, but they're not. You're not shown how to draw it, unfortunately, in here. I don't know how they came to this drawing, and they must have used circles or just mathematical calculations on a computer. I don't know. But now we know how to do it with a circle template based on the seed of life, because it's a hexagon and the seed of life draws hexagons. So we just need to add the golden circles to divide the edges into the golden ratio. And cool thing is we can draw all the forms too and not just build them. So it's a very multifaceted way of relating to sacred geometry on the physical plane, at least. Okay, so here I am going to make the nolid, and it's going to create 30 vertices. So I printed all these out, different color, and this is basically, I didn't know how, I just decided to do it this way. I tried a few other experiments. There wasn't a guidebook that I had that showed me how to do it, but I figured if I printed these out, cut out these triangular shaped wedges, anybody could do at home just by drawing the golden circle seed of life. Folding these in, it's going to create these little cones. And then it got interesting, and the tricky part was where the magic happened, really, when you ta-da and put it all together. You have to take those little cones, because each of those, when they're folded up, are creating the funnels that the stars are going to make the pentagon in the middle. So this is basically every single one of those little triangular wedges that I showed you. It's kind of like dual purpose. It's part of the hexagon and making the pentagon, and they're all converging. I called it a colorful convergence on my Facebook post, because all those colors are just meeting right at the center. And this one is illustrating the hexagon. We could also illustrate the decagons, and I'm sure I haven't seen any of these yet. We could illustrate the square faces and what that would all look like on a convergence in there, which I guess is would be related to the compound of the 5 octahedra, which is related to the octahedra in the squares, this one here. So Anyway, that's the overall presentation. It's been just about a week and a half or so since I've been working on this specifically. I hope you enjoyed that and just flow that I'm sharing of how the sacred geometry just evolved and how it connected to other things. I had a whole bunch of other slides to share with you that I've been wanting to share about the Icosiedodecahedron for a while now. So I'm going to have to do a follow-up because there's more on the Icosiedodecahedron and especially how it relates to our biology, more on the cube octahedron and the relationship of that to our biology as well. So I'm just excited to share some more videos. So let's just do a little show and tell of the form in hand and the stars. It was a little tough to make sure everything, there's a lot of wiggle to this, and it's, you know, it's got some movement to it because each of these are 60 individual pieces that I put together, and we can kind of follow a hexagon around here as I'm just going along that edge right there. It's a little wavy, but I can live with the waviness of it because it's tough putting all these little triangles together. So that's one hexagon. We're actually making these pentagon faces that are all kind of meeting in the center as well. So it's just a really, I don't know, I feel like it was a very neat exploration. I never thought I'd ever create anything like this with sacred geometry, or that it was ever even in the Golden Circle's Seed of Life template. And really, it went from, you know, doing the drawing of this one here and building the form of the 30 Icosiedodecahedron form, which is essentially, you know, just picture this now, which is just one of potentially 6 that are in here. And I just don't know how to even think about beginning how to construct all those little pentagon star funnels, you know, going down to the center of this. It would be just totally, maybe 360 of these going down into the center of the form, 360. So 360 points into the center based in this form here. So great. I'm happy that I was able to share all that. A couple other things. If you are interested in learning to draw some of this, certainly not getting into this complexity, my Patreon Volume 1 guidebook to drawing new geometry is just about done. I'll be making an announcement on that. It's just a small 30-page kind of starter with plenty of drawing options in it. I'll be able to share that all with you soon. And but check out the Patreon, and I'll have a link for it. You can join the New Geometers Facebook group, and I'll be, you know, it's great. There are 2,000 members in that now, so I'm just really psyched about the sharing and the awesome community that's developed there. And, you know, I'm teaching the apprenticeship, which just started, so that got kicked off. If you're interested in that and want to ask questions about it, I'll be doing another one in the next couple months, so keep your eye out that on the website. So I really appreciate you watching this video. If you like the video and the content here, please subscribe, and much love, and I'll see you next time. Bye.